look at that. Recording has started. This is great. And so other people will continue to log on. There are already 20 people with us. So Joel, if you want to introduce yourself briefly and talk about just how many PET scanners you've made, and then basically do your slides.
Okay, sure. I don't have the number off the top of my head, but anyway, so I'm Joel Karp, and I'll be sharing the talk with Dave Mankoff, who'll join, I guess, for the latter part of the talk. So I've been at Penn since 1983, joined the group to develop PET instruments, and not coincidentally, Dave was actually a graduate student at the time, so we started off together, and we're ending up together in the same department, the same division, and slightly different roles. So I have been involved in developing PET instruments. I was hired by Gerd Muehliner, who initiated the program. I'll say a little bit about that in the beginning of the talk. Evolution of PET technology, both at Penn, but a little bit more broad than that, because I felt that would help lead into some of the thinking and the concepts that have gone into the PennPET Explorer, which is a large axial field of view system. So with that, let me initiate the talk. And if it's convenient, Anna Rose, do you want people to ask questions or just leave that for the end?
Sure, if it doesn't disrupt you, I think it's okay. It works all right.
Okay,
And
I don't have
Joel and Anna, I might suggest also, I know Joel's slides, so I can cover up a little bit of my screen. I'm happy to keep an eye on the chat line and then pass the questions on. Sometimes that can be a good way to do it. So either way works.
That sounds great. Yeah.
That's
I'm happy to be the chat monitor.
Okay. Okay. So if I hear you, Dave, I'll stop. Okay, let me start then. So I thought it would be good to start sort of in the beginning because, again, while everything has changed dramatically over the last 40 plus years, some of the concepts are very much still intact. The very earliest systems, this is actually starting out a bit before I joined the effort, started in Washington University and transitioned to UCLA today. Very much at a time when CT so the people.
I can't hear.
I think some people may need to
problem
mute
with
their
the audio.
Yeah, some people may need to mute their audio if they have it on.
Yeah, everybody should mute, please.
That would be great.
Unless you have a question, yeah.
Okay, let me continue. Okay, so the earliest PET systems developed as starting as single ring systems based on the same reconstruction technology that was incorporated into CT. And there's a very nice progression of image quality that you see evolving in the series of images. The first PET instrument that we had at Penn that was used for brain imaging, neurological research, was the PET-5. So I think that came over in about 1979, and that program started with Marty Rivich and others. But the big game changer here was development of a detector that you see a picture of in the lower left. This is referred to as the Casey Nutt, Mike Casey and Ron Nutt block detector that allowed these instruments to have not only good efficiency for stopping, but also higher resolution. And they used a technique that we refer to as anger logic by sharing the light among the crystals so you could have smaller crystal elements with larger photosensing detectors, these photomultiplier tubes. And what you'll see in a few slides is these instruments are primarily body instruments, but the latest one, the exact HR, was superseded by the HRRT, the brain instrument that you might be familiar with, that had even higher resolution than you're seeing here. So the program that we started to develop came out of the early work from Gerd Muehliner at the University of Chicago using scintillation or anger detectors that are still present in single photon instruments today. And the idea is that you could have two detectors rotating around the patient, but these detectors need to be thicker. But without collimation, it relied on 3D imaging techniques, which was very different than the other instruments that were being built from BGO because they didn't have the energy resolution required to have in open geometry. And this program developed into some commercial instruments. On the top right, you're seeing a evolution of the detector that had a better geometry and that it was curved rather than a flat detector. That was called the Si-PMS detector that was being sold in the late 1990s and early 2000. The images that you see on the bottom were an example of, while they're good quality images, they don't quite compare to what we have today. You see a Si-PMS and then a later development of the Allegro, which is a little bit better resolution, but the techniques that, sorry? The techniques that you see here that are important that were introduced are iterative reconstruction, which improve the image quality and today is present on all commercial instruments. Transmission scanning, at that time we used a cesium, a single source that was in some ways a precursor to CT today, and that afforded more accurate quantitation. There were some count rate limitations with sodium iodide, but at the time it was sufficient for FDG. And again, that's notable because today's commercial instruments are really fine-tuned for FDG imaging. And what we hope to do is to go beyond that with the newest long axial field of view instruments. And then again, there were some improvements that we made with new detector materials. At the time, we transitioned to GSO, which was also part of the GPET brain scanner, to move away from sodium iodide that had certain limitations.
Joel?
Yes.
I think we're getting a little bit of feedback, and I can see by looking at the line, whoever's on the line that's George Woody, if you could just mute your line, that would be great, because it's coming in periodically. Thank you.
I thought I did. Mute. Start sharing. Which line? No.
Maybe the moderator can mute the other lines or not. Okay, so let me continue. So right now I don't hear the feedback as much, or I do. Okay, so George, are you muted or not?
Yeah, I thought can you hear?
Yes.
Yes.
Okay, now it sounds better. So let me continue. So I've mentioned the GPET scanner, which Anna Rose and Chuck are very familiar with because we entered into this program collaboratively. There was funding available from ONDCP. This is early 2000, and very fortunate to be able to use that funding to develop this new technology and then apply it to the brain studies with Anna Rose and the treatment center group. And at the time, so somehow I lost my screen sharing. Do people see that or not? Something went wrong. Let me try again.
Yeah, we can see that it went wrong.
You can, so yeah, I don't, okay. All right. Now let me try to restart it.
Yeah, there you go. If you click it again, you'll probably make it work.
You are all ready. Stay in the meeting. Let me try to share again. Okay. We good?
Yeah.
Good.
Okay. So at the time, this was pushing towards higher resolution, and at the same time, with a smaller bore size, you improve sensitivity. These are representative brain images. I guess many of you know that we use this system for probably 15 plus years, and then when we took it out of the clinic, we transitioned it to large animal imaging with Bob Mack's program until recently, when finally the scanner stopped behaving, and used it for the monkey images. At the same time, very similar to the timing of the GPET, the Siemens really started out as a CTI group, developed an even higher resolution system, the HRRT, which took the evolution of the block detector one step further by using even smaller crystals, actually had a two-layer system so that they could reduce the parallax error from the depth of interaction and improve the spatial resolution below 3 millimeters. And then there were a number of papers that demonstrated what we knew intuitively, that higher spatial resolution and sensitivity with a dedicated PET also leads to improved quantification. And they did some nice studies comparing that to the whole body systems, the HR Plus that I mentioned earlier. I wanted to introduce one other concept that many of you should be familiar with, time of flight, because while this was developing 40 years ago in the early 1980s, this is actually what what has become routine for all commercial and clinical instruments, as well as what we've developed into the new large axial field of view system. So this too was a program that initiated at Washington University, but also in Leti in Grenoble, France, University of Texas, both within the time frame of the early 80s. These systems used a different type of scintillator. This was either cesium or barium fluoride because they have very fast timing properties. But at the time, they were focused mainly on very high count rate studies because it did not have the spatial resolution or the sensitivity that the BGO systems had. And you see a C11 palmitate study. There are also many oxygen flow studies that were performed with these instruments, but for clinical purposes could not compete against the higher sensitivity systems that were primarily made of BGO at the time. Nevertheless, the concepts that were developed then we've seen take hold in the last 10 years, and it was about 2005, 2006 that time of flight was reintroduced in a commercial venue. It was first Philips that reintroduced this. The detectors that were developed build upon the previous detectors using angular logic, but they're pixelated. The big game changer here is that the newer scintillation material, a lutetium-based scintillator, LSO or LYSO, allowed us to not only have high light output and high stopping power, but also the speed of the scintillator necessary to get the precise timing for time of flight. So all of this came together with the LSO, with the fact that we now had CT for attenuation correction, with iterative reconstruction methods, and again with 3D fully open geometry rather than having septa. So rather than leaving behind the techniques from the early 80s, all of them have been now incorporated into the newest systems. And while it may look subtle, to give you an appreciation of the benefits of time of flight on the images shown is that you can achieve both lower noise, as seen by the more uniform background in the liver region, as well as higher contrast, seen with the pointed arrow. And so it's kind of the best of both worlds. You get both high contrast and low noise with time of flight, whereas without time of flight, you're sort of forced to make a decision. It's one or the other, but not both, depending on how the reconstruction approach is applied. So again, kind of in this range of 2006 to 2010, the other vendors came into play, both Siemens and GE. Actually, we still own the Philips Ingenuity TF, and the hospital also has a Siemens MCT. So these are older instruments, but still very much viable in the commercial regime. And here's another way to show the examples that we have with the benefits with time of flight. The lighter patients, such as the one shown on the left, one can achieve very good quality and good quantitative uptake as measured by an SUV with a study that's under 8 minutes total, basically 1 minute per bed position as the bed translates. A heavier patient where there's a very significant amount of attenuation as well as increased scatter, you need to scan longer. And so this is close to 30-minute scan, but the quality of the study is far superior to what one would get without time of flight. And so with this, one would say, well, what do I need to make an improvement further? And the answer at that point became sort of evident to all of us, which is, well, improved timing resolution. So the systems built about 10 years ago had 500 to 600 picosecond timing resolution. There's a very well-known relationship shown on the plot on the right. The sensitivity gain as a function of timing resolution increases quite dramatically as the timing resolution improves. And that's because it is proportional to the inverse of the timing resolution. So while it's dependent on the size of the object, which is the patient, whether you're a thin patient, a 20 centimeter torso or 40, it still improves. But the better the timing resolution, the more impressive the gain. And that translates into both an improved signal to noise and an improved quantitative accuracy, which is to this group probably the most important aspect of getting better timing resolution, because it's quantitative accuracy that is really the key to improved PET imaging, particularly in the dynamic imaging regime. So I put up this bullet list of ways that we as physicists try to make improvements. It all boils down to reducing the statistical uncertainty and determining this timestamp. You can do that with newer scintillators. LSO has continued to improve since it was first introduced more than 20 years ago. Improved detector designs. Out of that list, I would say that monolithic detectors probably have the most practical application, and in fact, our newest Molecubes high resolution system in the small animal lab is made with monolithic detectors. And that doesn't have time of flight, but it has promised to have very good spatial as well as timing resolution. What I wanted to mention here, because it is more in the commercial regime right now, is the introduction of new photosensor technology, moving from the traditional photomultiplier tubes to solid state silicon photomultiplier tubes. So very, very briefly, this looks like a lot of technical information, but I think it can give you an appreciation that these silicon photomultipliers can be made quite efficiently and very compact. And so the picture that you're seeing on the right is an 8x8 array. So it's 32 millimeters by 32 millimeters, but it can now have 64 channels. And that was very difficult, if not impossible, to achieve in such a package with a vacuum tube photomultiplier. Each one of those elements is actually composed of thousands of microcells, and that's how you get a signal. It's a digital device, so if the number of the microcells that fire is proportional to the amount of energy in the light that's coming from the gamma, so it's a direct and proportional signal that you get. These can also be put into MR systems, and so you know that there are PET MR systems that can now be made with silicon photomultipliers. General Electric has such a device that's at Children's Hospital. But much more than the timing characteristics, which are very fast and favorable, is the fact that you can now make detectors that have the combination of high spatial resolution, high timing resolution, and very good stopping efficiency. The details of whether these are analog or digital devices, I just wanted to put there because I think many of you have probably heard the notion of digital PET. Digital PET just refers to the fact that it has a silicon photomultiplier, not whether it's an analog or a digital device. But that, again, is just terminology. They all basically work the same way. The details of where the electronics are is differentiating between whether it's an analog or a digital device, but suffice it to say that these new devices in the last 5 years have come down in price sufficiently that they are now incorporated into all of the new commercial systems that are available. So let me just speak of two of them. One is the Philips Vereos. So they were also, while they introduced time of flight early in the game, about 15 years ago, they also were very early to introduce the silicon photomultipliers. This is the system they call the Vereos PET-CT. And what is important about the way they did this is they did it by having a crystal array that is matched to the silicon photomultiplier array in a one-to-one coupling. And so there are 64 crystal elements and 64 channels in a very small compact package that is about 3.2 centimeters on each side. By doing that, they can achieve a time of flight resolution that at the time was far superior to what the photomultiplier tube systems offered. So this is 320 picoseconds, so not quite a factor of 2 better, but almost a factor of 2 better than the previous systems. And you can see some nice images that had been acquired at Ohio State University with a pre-production system to demonstrate that very short scans can be acquired. Again, this is a relatively light patient with a smallish BMI, but nevertheless, studies under 10 minutes were shown to be achievable with very good time of flight resolution. What is also important, this is now a presentation from the Philips group that had been made a number of years ago, is that not only is the performance of these devices stable, which wasn't quite demonstrated 5 years ago, so over time, the timing resolution is stable. What is really key is that the timing resolution is also very stable over count rate. And so the horizontal curve in the middle is with the silicon detectors with the new Vereos system, whereas the timing resolution in the other plot that you see is from the Gemini TF. You see quite a degradation over count rate, and the timing resolution at the low end, which is appropriate for FDG imaging, may not be applicable to higher count rate imaging with much higher activities or short-lived isotopes where we very often inject higher activities. I also wanted to mention the Siemens system. So this is now the newest time of flight system with silicon photomultipliers, and they took advantage of a few extra years to develop a system that has superior performance, higher spatial resolution with smaller crystals. So the spatial resolution is about 3.7 millimeters. So that's quite an improvement on previous systems. They achieved the best timing resolution of any commercial system right now, which is 215 picoseconds. So that's now more than a factor of 2 better than the previous systems. And also decided to extend the axial field of view a bit more than previous systems, so that's 26 centimeters. So again, still applicable to multi-bed or continuous bed translation for FDG imaging, but it pushes the envelope a bit upon the higher sensitivity that one can achieve with a longer axial field of view. Again, keeping in mind all systems today have no septa, so they take advantage of the 3D geometry. The two images that you see on the right, taken at HUP, are examples of what one can do with a very heavy patient now with very high BMI. Again, the improved timing resolution is very beneficial, particularly for the heavy patients. And this is a scan acquired in only 11 minutes, whereas the one that I had shown earlier from the Philips Gemini was 27 minutes to get reasonably good image quality. So that's a consequence of now having timing resolution that's a factor of 2 better, as well as higher sensitivity intrinsic from the longer axial field of view. And example of a brain study. So again, keeping in mind that this system has under 4 millimeter spatial resolution, one can also get very good quality with a 10-minute scan for FDG. So one might ask then, although I think the answer becomes quite evident at this point, why total body PET? What are the advantages? Why not stick with the kind of commercial systems that are currently available? Well, you can only make a system sensitive up to a certain point. With the crystal, one can make it thicker, but then there's the point of diminishing return. They can't be made too much thicker. It not only costs more, but the gains are not linear anymore once you get beyond the crystal thickness that is in current machines. Really the most obvious, but also the most effective way to improve sensitivity is to make it longer. Obviously with a cost, but the benefits go beyond just sensitivity. So we realize that the commercial systems that require multi-bed, or as Siemens has implemented a continuous bed motion, are very effective for a tracer such as FDG, which doesn't quite plateau at an hour, but at least reaches a certain type of stabilization, and one can, if one adheres to a specific regimen of acquiring all patients at 1 hour, gets a certain level of a quantitative accuracy or tries to minimize the biological variations. But again, you can obviously not achieve good dynamic information over the whole body at once, as you can with a single bed position. So this is a little bit, lot of information in these bottom plots, but I just really want to make two very important points as you make the scanner longer. The first is that the plot on the left shows the increased sensitivity for a point source, but consider that to be representative of a small organ. It could be the heart, it could be the brain. So for a relatively small organ, the improvements in sensitivity only increase up to about a factor of 3, at least if we're talking about something that's approximately a 20 centimeter size, for example, a structure within the brain, figuring that the brain is about 20 centimeters of attenuation. So once you get beyond 70 or beyond 1 meter, those improvements saturate and they level off at about a factor of 3. That relates to the improvement in signal to noise one can get for, let's again use the example of brain imaging, or the improvement in quantitative accuracy. The very large improvements that one gets are considering a uniform source in the body, and you see that those improvements can go as high as a factor of 10 for a 70 centimeter long system, or a factor of 30 to 40 for a 140 centimeter long system, because again, you're putting the activity into a large body, and instead of moving it along, it's all being acquired simultaneously. So the way that I would express that is that relates to the ability to reduce the dose, if again thinking about a clinical study or even a research study, or the ability to scan shorter. But again, the signal to noise improvement would be more related to this factor of 3 that we see. So where the real interest is if we start to think about research and translational applications, and I think at this point many are aware that we have a system that we've built at the University of Pennsylvania, but there's a very active program at the University of California at Davis. They have an even longer instrument that we do. They have an almost 2 meter long system. So what you're seeing on the right is an image taken from their system, the United Imaging Explorer. And so in addition to reducing dose and scan time and being able to achieve delayed imaging, and Dave will say a few words about that in a couple of minutes, we also have the ability to simultaneously image very large volumes, look at biodistribution of new tracers and dynamic imaging of multi-organ systems. Obviously, the brain-body interactions would be of great interest to this group, and also to improve the quantitative accuracy of kinetic modeling. I would say whether or not you're doing that for a single organ or for multiple organs, because you're getting as many as 3 times more counts per organ. So I think that's a big deal to not only improve the quantification, but also look at these dynamic distributions or time activity curves for multiple organs simultaneously. So just a couple of words, get back into the details for just this slide. How does one do that? So I tried to speak a little bit about the different ways of designing detectors, and these detectors do not deviate very far from detectors that have been implemented commercially. The one from the U Explorer, which is United Imaging from Shanghai, China, is the one developed at in China and is now cited at UC Davis. So they use something which is a bit of a variant on the Anger logic, using a small number of silicon photomultipliers with a densely packed pixelated array of crystals. So there's almost a 10-to-1 encoding. That is designed to save a bit of cost on the number of silicon photomultipliers that are required. And you can see there's a bit of a Anger logic type block flood. So the resolution is inherently about 3 millimeters, but you don't get as good timing resolution with this type of device because of the light sharing. The system that we built, and this is with a lot of support from Philips, using their detectors, is based on the same detector technology that is in the Vereos scanner. And this uses the 1-to-1 coupling. So you see here, you not only get very, very fine spatial discrimination shown in this 2D flood, almost perfect crystal identification, but also an improvement of timing, 250 picoseconds, with about 4 millimeter or just a shade under 4 millimeter spatial resolution. So again, these systems are longer, but they are very much leveraging the technology that has been designed into commercial systems. So I wanted to show one image. Dave will speak more about some other images, but I thought this introductory image would be helpful. So we did a very small pilot study while the system had 3 rings or about 70 centimeter axial field of view last year while the system was in the lab. This is actually our first and second human subjects, both FDG. The first one is shown just to demonstrate that the average scan time of 16 minutes leads to a very high quality, very high statistics image, whereas with only 2 minutes, by subsampling the data, we get something which looks a bit more close in quality, while still very good. But the statistical quality that we have with a commercial instrument designed with about a 20 to 25 centimeter axial field of view, and we obviously acquire many more counts within the 2-minute scan than you can acquire with a shorter axial field of view. And in fact, the series of cross sections through the liver on the left shows that even down to 1 or 2 minutes, the noise is relatively modest, and one can imagine, again, I would let a clinician interpret that this is a normal liver, so you're not looking at lesions, but seems to be quite acceptable. The study on the right, I wanted to also show that we not only get good statistics, but I think very good image quality, very good spatial discrimination, as seen particularly not just in the papillary muscle, in the heart and the cross-section through the vessels, but also the structure in the spinal column and in the brain. Again, these are 2 separate acquisitions. The top one of the transverse sagittal coronal view of the brain was with the brain up near the edge of the field of view, and so that has somewhat smaller statistics than by moving the subject down into the center of the field of view where the sensitivity is highest. You see that there is no real difference in the spatial resolution between the two, but of course there are more counts when you put it centered in the field of view, and this is part of the reason why we've extended it beyond 70 centimeters in order to achieve both good spatial resolution as well as the highest sensitivity over a much larger axial coverage, which you should be able to do once this is beyond 1 meter long. And so let me wrap up in the next 2 slides. So we, just before the virus hit us and partially shut down the university, we had just gotten to the point that you see here. This is the new facility that was constructed last summer. We moved in I guess it was the September-October timeframe, and we essentially disassembled the prototype and put it back together, but now with an additional number of rings. The pictures that you're looking at have 5 rings. We plan to add 1 more to make it a 6th ring, but except for the fact that we didn't yet put the covers on, the system is just about ready to go, given a relatively short period for us to go back, turn things back on, and just, of course, double check that everything is working. Of course, it now has a CT, so that we can get the anatomic registration and use the CT for attenuation correction. But this is, again, literally just about ready for human imaging. And this is the last slide I wanted to say a few words about before transitioning over to Dave, speaking a little bit more about the program. It's very important that once we complete the 6 rings, we're certainly going to do our job as physicists and perform an acceptance testing. We know that we've built and designed the system, but we'll still make sure that it passes the standard tests. This is typically done. We've actually completed the CT. We'll do the PET again as soon as we get back to the lab. We'll follow the NEMA prescription so that we can specify the performance, but we also know that it's meeting its design characteristics. It's also important to know that we will be performing essentially the same type of quantitative calibrations that we do for all of the clinical instruments. This typically involves an ACR phantom where we double check the SUV in the cylinders, uniform background. We have a program already in place to do routine QC. And so to the best of our ability, we will ensure that we have appropriate quantitative accuracy, certainly as good as, or hopefully even superior to what we have in the clinic. When I say superior, not that our methods are better, but we will be acquiring data with a superior number of counts and overall better performance. So we should be able to achieve that for all of these studies. And we have again, this is designed principally as a research instrument. So we have the IRBs in place to allow us to do the human research. We will naturally try to emphasize applications that both take advantage of the whole body characteristics, but potentially can also leverage the fact that the brain and the body will simultaneously be in the field of view. And so there have been a number of interesting ideas that have been put forth to do such studies. And obviously we would welcome that involvement from everybody in your group as well as from others. So, Dave, this is a good time for me to take a break. You can see if it's best to take questions or if you'd like to follow on with the rest of the lecture.
I had sent out a chat for questions, but I didn't get any responses. So
Okay.
It's not a very e-chatty group. Does anybody have questions for Joel? I'm going to finish off relatively quickly and show you some more imaging work that's relevant to more of the dynamic quantitative imaging. That's
Joel?
Yes.
Joe, this is Bob. Yeah, I didn't realize that there was such a large difference in the timing or temporal resolution between the Davis Explorer and the PET Explorer. I think most of the people on the call are familiar with improved spatial resolution, but I think if you could just explain how having an improved timing resolution, how that impacts image quality in the data you acquire.
Sure. So it turns out it is approximately a factor of 2. It's a combination of the silicon photomultipliers that we're using, and partly in the detector design, which I mentioned, the fact that interesting that maybe somewhat ironic for us, because we started our program with the maximum amount of anger sharing, light sharing, and now we have the minimum amount in this new detector with a 1-to-1 coupling. So in effect, we've gone back to the original design of the WashU group from Turbogosian, except that we now can use much smaller crystals and much smaller photosensors, whereas at the time he only had large tubes. How that will affect the data, time of flight improves everything. It improves effectively the sensitivity, so a factor of 2 improvement in timing resolution translate to an effective improvement in sensitivity by a factor of 2 by virtue of the fact that you reduce the variance in the images. It also improves the quality in such a way that for local distributions you're much less sensitive, or it's a way of getting a localized reconstruction. So if you have effects of high activity distributions or high attenuation that are distant in the body, if you have a better timing resolution, you will be completely insensitive to that. And so these are some of the ways that the timing resolution not only improves your overall sensitivity, but also the localized signal to noise and mitigation of any effects from both attenuation and activity distributions. It also reduces artifacts, which generally we don't suffer from. So in general, I hope I've answered that question. It is good. I think that, differences of 50 picoseconds or so would probably not be that noticeable, but a factor of 2, I think, will become apparent in the quality of the images.
I just wanted to say that's exciting anytime that you can think about having something that maintains resolution or actually improves it and is shorter. It gives you more flexibility for your clinical protocols, where obviously target organ exposures is a limiting factor on how many scans you can do within a participant within a unit of time, like a year. And so for repeated measure designs, being able to have this increased sensitivity, it's extraordinary to be able to have short scans. In addition, of course, on top of that is being able to see brain and body at the same time. So
Right.
that for the neuroinflammatory protocols, with Bob's neuroinflammation tracer, being able to look with the HIV OUD protocol eventually, and with Reagan's OUD and lung, it just opens extraordinary opportunities. I'm sure Dave will talk more about that. Yeah.
Okay, shall we move on, Dave? And come back to questions at the end again?
I managed to get myself on and off of mute inadvertently. And Rose, I was just going to follow up with what you said. Is there's a couple of ways of playing this. One is to be able to take on better images, especially dynamic images at standard dosing. The other thing is these days there's been some improvement in the technology of the CT so that the radiation dose actually now again comes substantially from the emission portion. That wasn't always true. So if you have a subject needing a number of scans, then you always have the option, if the radiation dose is the rate limiting process, this scanner is going to allow you to go this at quite low radiation doses, and this has pediatricians quite excited because it may provide a situation for a variety of reasons to really reduce dose and risk for pediatric patients.
Absolutely. I mean,
Okay, so I'm gonna take over here, and I want to acknowledge, in addition to Joel, there are a number of folks on the work here that have contributed to it. Aaron, Robert Dude, and others, as well as Austin Pantel, who's been working in this, Barsha Visnawath, and in particular, some of what you're going to see is related to the work that Joel's been doing on the Explorer, primarily with Austin as the primary clinician, and then he and I share a Cancer Moonshot grant that allows us to explore some concepts in how we do dynamic imaging. I actually think those are probably quite relevant to the types of things that are likely to be done under the P30. But we can't help ourselves as clinicians. Here's just a couple of early clinical PET scans results. You can see a patient on the left of your screen who had a clinical PET CT scan, that is with one of our regular scanners. I think it's mostly the Philips Ingenuity. And we image them at 2.75 hours and 4.25 hours, where we're way out to much shorter doses, where we not only get higher image quality and I think better resolution, but it's a well-known trick that in most cancers, background non-incorporated FDG will go out of the way and the cancer will hold on to the FDG, and you can see some improved contrast and definition in addition to improved spatial resolution. We'll come back to that later. And again, you're doing the whole body in 10 minutes here and actually getting a much better image. Next slide. So I think when we really start to get into what's relevant for the type of work that you're doing in the P30, this scan provides an exciting indication of what can be done. So this was somebody who was injected on the table. There's a little bit of a tour de force doing this in the lab that was building the scanner. We now have a dedicated scanning facility you saw. And in particular, this almost looks like a nuclear angiogram at high resolution, almost like you'd expect to see from an MR. And you can see the evolution of this injection from the earliest part of the injection into the left arm, all the way through the heart and through the lungs and back again and up to that thing called the brain at the top, and you're actually starting to see some significant FDG accumulation over time. So in addition to these really pretty pictures, which we like to show off the instrument, you get very high quality quantitative information, which you can see down below. Not only the bolus, where actually probably some of the spiking we see is not necessarily noise, but actually spiking in our injection. And at a lower scale, you can see the high quality of the data that we're getting in the different structures. Next scan, please. So this image shows some very interesting properties and gets to a debate that's been going on for some time. So I just want to walk you through it for a second. This is a patient who was imaged from head down to mid-torso starting early after injection and coming back all the way to almost a full day. And so for those that that are not used to seeing this, 24 hours is approximately 12 half-lives of the radiopharmaceutical. And so this is an extraordinarily low concentration of tracer, and in fact the image quality is not great, but it illustrates something actually very exciting, and we have some other pictures that have shown this just maybe a little bit better on the brain, is if you see this patient who has uptake in the myocardium, which was done on purpose. If you have a little bit of food, and especially sugar, while you're getting the injection, insulin will drive uptake into the myocardium, which it wouldn't normally do. And so if you visually compare the intensity of the myocardium to the brain over time, you can see maybe by the time you get to about 5 hours, you're starting to see the myocardium look a little brighter than the brain. And by the time you get to 24 hours, and you can see this as early as 18 hours a little bit more clearly, you actually see washout of the normal brain. Going back to basic physiology, this was argued about for years for those that have been in Penn as long as many of us have that have seen this debate at its inception, is the extent to which FDG is dephosphorylated. In tumors, it's actually not dephosphorylated pretty well because most tumors don't have those enzymes. But in glycogen-using tissues such as the brain, you actually get fairly significant dephosphorylation because in order to be able to use glycogen, you need to dephosphorylate glucose 6P. And what you see is actually wash out of the brain towards the end of the study. This looks even more dramatic in monkeys, as the Davis folks have shown us. And you see retention in the myocardium, which is not particularly a glycogen user and an FDG dephosphorylator, showing your ability to find extraordinary kinetics and get at things like K4 in ways that we've never been able to do before with FDG. And you can begin to imagine the applications this could have to early tracer development and the nuanced tracer kinetics. And even for a sloppy cancer modeler like me, these are really exciting opportunities. And again, you can see the quality of the data that you can get. Next slide, please. So I'm going to now go back to some of the stuff that we are working on as part of the work I do in breast cancer and as part of our cancer moonshot. And this takes you back to work that has been developed in cancer metabolism. A lot of that work was done here by Craig Thompson to begin with and later by Chi Dang, showing that in addition, and Joel, if you hit the space bar, this has a little bit of animation, that in addition to glucose, you can actually have tumors that burn glutamine. And we're actually still figuring out exactly why tumors would burn this amino acid, but the ones that do are aggressive, highly resistant to treatment. And it's a significant survival advantage for these tumors that use the glutamine to be able to provide resistance to chemotherapy, recurrence possibly involved in dormancy, and recurrence of tumors. So a rather important process. And so we can look at many of these tumors, and in cancer at least, it's not like they use one fuel or the other. Those tumors that have figured out how to burn glutamine are burning glucose like crazy, and the ability to move back and forth between those two fuels is an important part of the survival mechanism that we're still figuring out. So next slide, please. So we're using an analog that Hank Kung developed called fluoroglutamine. This is a substrate that is transported like glutamine into cells. It is not metabolized by glutaminase, which would be the first step in that pathway that I showed you. And so we're basically measuring the volume of distribution of fluoroglutamine. Those cancers that use a lot of glutamine suck that glutamine out of the cell and have very small pools and would actually show up as rather faint. Those tumors that were more aggressive were less aggressive and weren't burning glutamine would actually have higher pool sizes and show up better on these scans. And in fact, some of this has been seen in some of the early work. So in general, when we interpret these studies, because of the nature of the glutamine signal, we're always going to need to interpret that in the context of another signal, and in particular, a direct comparison of glutamine to FDG, in this case, glutaminolysis to glycolysis, shows us what we're looking for, and that is in particular that relative to some mean glutamine turns out rather faint compared to FDG, this one being somewhere in the middle of around that mean. And this is an ongoing study by Austin Pantel, who was just getting this trial open just about when COVID hit, and we've now imaged 3 patients, but getting some very interesting results. The next slide, please. So what we proposed in our Moonshot grant was to take advantage of this large volume PET tomograph and its unique sensitivity to do sequential injections that are low-high tracer. We chose to do the fluoroglutamine first because it washes out over time, and so we get a selective advantage if we're giving the FDG second. And for those that might be familiar with cardiac imaging and the way we've done cardiac stress tests, we can use a low-high injection to get a hybrid curve that would allow us to view both techniques. And we're pretty sure we can model the end of this relatively simple fluoroglutamine kinetics to the point where we can reliably model these two simultaneously. So the proposed approach, and we hope to do this relatively soon after the system comes back up and we come out of precautions, is to be able to do these 2 injections sequentially and come up with parametric images and metabolic heterogeneity. And again, I think for your studies and the fact that there may be situations in which you need combinations of 2 tracers, having this capability, which can be used in a conventional system, provides a lot more flexibility, and I think is ultimately going to provide a lot higher image quality and capabilities compared to what we're doing. I want to show you just 2 more slides on some of the early results from our some of the outputs of our moonshots. If you'll go to the next one, Joel. One of the things you can do when you get more data, and this has been done for many years, including back to when I was a graduate student and John Ollinger was here and had done some of this work in his Ph.D. thesis, is there are situations in which you can actually build some of the kinetic analysis and the time domain analysis into the actual algorithm. And when you have these high data qualities, it makes even more sense. And this has been combined by Samuel Mateja and his group into the form of the direct algorithm, which is a highly efficient algorithm that is nicely designed for the size of data sets that we get here. And in fact, you can build the time domain into the scan and only have more efficient reconstruction and production of parametric images. But in fact, you can, if done in certain ways, apply some biologic constraints in addition to physical constraints in the model and improve the image quality, and we think the quality of the quantitative data significantly. This has also been done with post-reconstruction methods. We've been working with Finbar O'Sullivan, a longtime collaborator back from my days in Seattle, who's been doing post hoc approaches through a mixture analysis approach where, again, the biologic constraints that can be provided by the image can provide a very efficient modeling system and a significant improvement in image quality, as you can see from these approaches. And then finally, as part of this Moonshot grant, we had the opportunity to work with Despina Cantos and her graduate student, Ria Chitalia. And many of you may not know Despina. She's part of our really very outstanding artificial intelligence and radiomics group that does data science in the Department of Radiology. She's done this mostly in conjunction with standard breast imaging like MRI and mammography, but she's now applied this to some of these dynamic images in which you can look at this as a 4-dimensional time set and begin to pull out radiomic features and do some learning to identify what the principal components are. And in fact, in a paper that's under construction as we speak, she took a data set that I had been working on for 15 years, a dynamic breast cancer data set from the University of Washington, and pulled out a recurrence-free survival predictive signature that I hadn't found in 10 to 15 years of trying to find it by more conventional modeling. So I'm going to close there and say that I think that this system, in addition to providing really pretty pictures, low-dose imaging, fast, efficient imaging, the ability to image both brain and body, is really going to provide us, I think, with high data quality that's going to give us some unique opportunities for thinking about how to acquire and analyze our images. And Joel, I think that was the last slide, if I remember correctly.
Yes.
So maybe if you want to stop screen sharing, we can go back to looking at each other, and I'm happy to take questions. And there we see Joel. I have noticed, by the way, I said this on another call today, is that this COVID precaution seems to be engendering a lot of very good-looking facial hair, at least for those that can. I don't want to be too sexist in that claim.
Dave, it's a good way to keep people 6 feet away.
There you go. All right. So thank you, Joel, and thank you, Anna Rose, for the opportunity to present these exciting data.
Thank you both so much. It's very inspirational, and even for those of us who are not nearly physicists or biophysicists or even extraordinarily experienced radiology investigators as yourself, you can appreciate the possibilities. So it's pretty exciting. And when you marry it with the ligand development that's ongoing, it's just, well, it's a really a special time.